I'm going to say something more about lazy evaluation. This is new things. These are things that are not in the book. So it's important to look carefully at what I write on the board. And I'm going to talk about lazy suspensions. So last week I showed you weight needed, and I showed you lazy functions. And we made some lazy programs. But it's very easy to forget how it works, because all you have to do is take a function and write fun and lazy. So in this course, I want you to really understand it. So we're going to look closely at what happens during the execution of a lazy program. So that's why I'm going to talk about lazy suspensions. And we'll talk some about Hamming. So we'll go revisit the Hamming, but we look at how it executes. How it executes exactly. How the execution is triggered exactly by the need for printing the result. And then I'll talk a little bit more. I'll talk about monolithic versus incremental. This is some functions, you cannot make them lazy. If you want the first element, sometimes you have to calculate the whole thing. There's no way to make it lazy, really. These are called monolithic. And the functions that you can make lazy easily are called incremental. And final example is lazy quicksort. This is where the lazy evaluation is able to invent an algorithm. So this is showing the power of lazy evaluation. So lazy, it seems very easy, but in fact it's incredibly powerful. So I want to show you some of that power. So here I'm going to show you some of that power, and then in the next course we're going to show even more power, show how you can invent, you can make very efficient algorithms using laziness. So laziness is an extremely powerful technique, much more powerful than you imagine when I talked about it last week. Okay? So most of this, the first parts, will be done on the board, will not be done on the screen. The lazy quicksort I will be writing code, but also do on the board. So today is a little bit more theoretical course than last week. Let me talk about lazy suspensions. So let's go again to the simple function that creates a lazy list of integers, ints n. Very simple. N bar ints n plus 1. Okay? So this looks extremely simple when you use it. But in fact, a lot of things happen when it's executing. So we're going to look at that. So this is actually translated as follows. So I'm going to give you the kernel language translation, which gives the semantics of this. So the function becomes a procedure. I create a thread. The thread does weight needed. Maybe I wrote this down a little bit. Weight needed R on the result. Then I have R is equal to the function body. I will not translate that one into kernel. That's not important right now. So I will keep it as it was. Okay, so I have a thread, and inside that thread, I'm doing weight needed. So if I call xs equal ints of 1, for example, this will create a suspended thread waiting on the weight needed. Okay, so I'm going to give that a name. I'm going to call that a lazy suspension. So a lazy suspension is a thread suspending on weight needed. Okay, so I'm going to call that a lazy suspension, and I'm going to make a picture. So here's the variable xs to this potentially infinite stream, and the lazy suspension is attached to it, so I write it like this. So here is the body of the function. So this is a lazy suspension attached to a variable. So when I need the variable here, I will execute this, and the result of this will be bound to xs. Okay? So for example, if I do something like browse xs.1, so the dot operation is like an addition or a case. It needs its first argument. So this will cause the weight needed of xs to execute. Okay? So what happens is we're going to have the result. So we're going to execute xs is equal to, and it'll be 1 followed by ints of 1 plus 1. So this is what we're going to execute in its own thread. Okay? Now let me write this a little bit more specifically. 1 bar xs prime. Let me introduce this hidden variable, because this variable is there. Xs prime is equal to ints 1 plus 1. So this will execute in its own thread. So I will bind xs here to 1 bar xs prime. And then I will call xs prime is equal to ints. Again, the same lazy function. So what happens is I'm creating a new lazy suspension. So when I activate this lazy suspension, I bind xs, and here I'm creating a new one. So the result is xs will be equal to 1 bar xs prime. I can write it like this. Let me put a box around xs. And I will have a new lazy suspension, which I can write again like this. So this new lazy suspension will be ints of 2. So this new lazy suspension will create another thread, another weight needed, and do 2 bar ints 2 plus 1. Okay? So this is transformed into this. See how it works? It's very simple. In fact, we know already. But it's important, I want you to get a good understanding. So this is a simple case where I activate one lazy suspension, and then I bind the variable and I create a new one, because I have a recursive call. Okay? And if I keep going, if I do another one, browse xs.2.1, then I will in fact get the second element of the list. This operation, xs.2 is equal to xs prime. This will do xs prime.1, so it will activate again the lazy suspension. So I will have another unfolding. So I will do it like this. So the result will be something like this. Okay? So you can see that eventually I have a list, or stream actually, where at the very end there's a lazy suspension. And each time I ask for more, the list will unfold a little bit more, but always at the end there's going to be a lazy suspension. Okay? And this one will sit there waiting until I need the result. So this is how the laziness works. It's always at the end of the data structure that I have lazy things. So if I have a lazy list, I have elements, A0, A1, A2, AN, And at the very end, I will have a lazy suspension. Now, we can also have lazy trees. I haven't done an example yet with a lazy tree. A lazy tree is where the whole frontier of the tree is being created. So, for example, I can have an element. And here's a binary tree. And at the frontier of this, I will have again variables. S1, S2, S3, S4, S5, S6, S7, S8. And each one of these will have a lazy suspension attached. Okay? So the whole frontier of the tree, the frontier, which is the edge of the tree, will have all lazy suspensions. So in a list it's very simple because there's only one lazy suspension. Yes, question?
Je me demandais si le nombre de lazy suspensions, ça ralentissait l'exécution du programme.
Le nombre de lazy suspensions. So let me translate to English. So the question is, does making a large number of lazy suspensions slow down the execution? Well, it's clear that a lazy suspension creates a thread. So lazy execution has an overhead, okay? So you pay a price of this very nice infinite structure is that you will be creating lazy suspensions. Now in Oz and Mozart system, the lazy suspensions are like threads. So threads are very lightweight. So you can create very many of these, thousands, 100,000. But still, it's much more expensive than just a variable. Okay, so you are paying a price for this. But it's a constant factor. There's no, you're not changing the complexity. Okay, question?
So is it interesting for some problem to use a lazy tree? Or
Yes, it is interesting because again, it's like a lazy list. You have an infinite tree, but you only compute the part of the tree you really need. Okay. So I don't have an example right away, but there are many examples of infinite data structure using lazy execution that you can find on Google and so on. Huh? So yeah, it's not always interesting, huh, to have lazy trees. But sometimes it's very interesting. It's interesting when you do not know in advance how much you need. Then it's very interesting. Here, if I don't know in advance how much of this list I will need, then laziness is a perfect solution. Okay? If you want your program to be dynamic, incremental, where you don't know when you write the program how much you will need, then the laziness is perfect. Then it's really a good technique. Okay? And the laziness will automatically do the minimum amount of computation. And it also makes the program simpler. Okay? So that's a simple example. Let me now go back. Let me now connect lazy suspensions together. So this example has one lazy suspension. Let me now show an example where there are many lazy suspensions connected together. That will be the Hamming problem, which we've seen. So let me show how it works in terms of lazy suspensions. In lazy lists, like in the ints example, we have one lazy suspension. So we have one lazy suspension. In the ints example. But let's show an example where we have multiple lazy suspensions. So in order to do that, let me again show you the Hamming. Go back to the Hamming problem we did last week. So remember the Hamming problem, let me just write the equation that is the main loop of the Hamming problem. H is equal to 1 bar merge times 2h. That's the first argument. And the second argument is another call to merge times 3h times 5h. Okay? And then 2 brackets to close. So this is the main loop of the merge, of the Hamming problem. And we can see that, let me recapitulate. So we have lazy functions, merge. So the merge function will basically do a case on S1, S2 to get elements. S1, S2 of H1 bar T1, H2 bar T2. Then I'm not going to write the whole code, just show you the main loop, because we'll use this. And the times also has a simple loop, a case statement. So this is H times n followed by times Tn and inside the merge here, there's going to be a recursive call. For example, T1, S2, or whatever. There's a recursive call inside. Okay? So this is the equation. So when this is started, when you call this, you're going to create 5 lazy suspensions. So let me write that down now. Let me make some space. So H is equal to 1 bar H prime. So all the hidden variables, I'm going to show them here. There are in the kernel form hidden variables for all the functions here. So H prime is the first hidden variable. So H prime has a lazy suspension. Okay, this lazy suspension will be this merge call. Okay, so let me see what's the best way. Let me write it like this to show all the variables. Let me create let me unroll this. So the merge here has a variable times 2h, which is t, which is given by the result of times 2h, and m, which is the result of the second merge call. So the t will be times 2h, and the m will be, again, merge, we call it uv. The u will be times 3h, and the v will be times 5h. Okay, you can see then we have here a graph of lazy suspensions. So these variables here, I'm not going to write them over again. So I have h prime going to lazy suspension. This lazy suspension has 2 inputs, t and m, this merge call, which means 2 other lazy suspensions. This one has 2 more. So there's 5 in all. Okay? Now we're going to show what happens when we execute this. So now let's do browse h prime dot 1. So this is going to display the second element, but this will cause the lazy suspension to activate. So how does this work exactly? Now we have this whole graph here. So you're going to see the activations will kind of percolate. They will flow through the system. So the first lazy suspension that activates is this one, is the merge. Okay, so if you look at the merge here, this one is going to activate. So this one will execute. So the body will execute. Okay? Well, here we'll execute. So H prime dot 1, the wait needed here activates. I execute the body here in its own thread. So this is the result. So basically I made it execute H prime is equal to the body, which I'll write down here, S1, S2 of T1, H1, T2, H2, then, okay, I'm writing it down small here. So I do this. You see that? I'm doing this in its own thread. That's very simple, right? You see that, huh? Well, now we have a kind of a domino effect where we're going to trigger more lazy suspensions. So we have a case statement here of S1, S2. But what are S1 and S2? It's actually T and M, huh? S1 and S2, huh? It's actually T and M. Let me make a different color. Because the arguments of merge are T and M. So actually I have here T and M. And here I want the first element of T, and here I want the first element of M. You see that, huh? So what happens is, this case will need the first element of T, and it will need the first element of M. That means this case will trigger these two lazy suspensions. So you see how it works, huh? The body of the merge here has a case statement, and this case needs more. It needs information. It's hungry. It wants information. So in order to get that information, it has to activate these two lazy suspensions. Okay, so that will cause two new lazy suspensions to be activated. So activates two lazy suspensions. So what happens is we have T now is equal to that. T is equal to times of 2H, which is this thing here. T is equal to case, and its argument, I'm sorry, I switched the arguments here. It should be NS. The H is now the argument. So it's going to be H of, and then an element followed by H prime, then there's a recursive call end. This H is the same as the original H. Question?
Je me demandais si il y avait des optimisations pour éviter l'overhead en utilisant le même thread.
Oui. So the question is, can you optimize this so that you reuse the same threads so you're not creating new threads all the time? The answer is absolutely yes. You can do lots of optimizations. You can, of course, reuse threads for the recursive call, like for ints, for example. The recursive call, there's a, if you can actually program it directly using wait needed in the same thread. Okay. So I'm not going to talk about these optimizations now, but it's clear that the overhead here, where you create a thread for each lazy suspension, that you can do a lot better by doing optimization. Okay? But that makes the code more complicated, so I'm not going to show here. But you can make it much more efficient by doing that. Okay? And a smart system like Haskell will do lots of optimizations. So the laziness at the end of the day is not so expensive, actually. Okay? So let me go on now to explain how it runs here. So H prime will be bound to the body of the merge call, which needs T and M. This calls the T and M lazy suspensions to be activated. Now note what happens here. We have T is equal to the body of the times, and the case is now using H. But the H is known. So the E here is already equal to 1. And this H prime is the H prime. So this T, this body, will not create any more activations Okay, it will execute the body, but it does not have to activate any more lazy suspensions. Okay, so the activation stops here, and this one does not activate. So now if you look at M is again a merge call, so let me show the body here. In case the two arguments of this merge are U and V, so let me write U and V here. So there's a body here which executes with U and V. Okay, when I activate M in its own thread, now again I have U and V which are needed. I need the first element of U, the first element of V. So that means these two times calls will also be activated. You see that, huh? But the times call is reading H. So it will not activate anymore. So you can see how there's kind of a chain. I start with doing one thing here. I want one thing. I do one small instruction here. One instruction. And this will trigger a whole chain of actions. So this instruction will execute this. This will cause these two to be executed. This one, this M, will cause even two more to be executed. So all of the lazy suspensions are activated. Boom, boom, boom. You see how the chain works, huh? I need H prime, but executing this body will need more information, T and M. So there's like a chain of activation. So all of these lazy suspensions get activated. They all run the bodies. And then what happens? Then we get results. Okay? The T, it knows E. So the E is going to be equal to 1. Okay? And here it'll be 2 times 1. So it'll do 2 times 1 with a recursive call times 2H prime. So here I've, let me make it nice, 2 times 1 followed by times 2H prime. And then these two will also activate. So let me write down now the activations, the executions, and what happens. So we're halfway done now in the execution. You can see this small thing causes many things to happen. The first thing that happens is that all these lazy suspensions are activated. So that's the first thing. And the second thing is now they all execute. So we will have T is equal to 2 bar times 2H prime. Okay? Let me write it like this. 2 bar T prime, and T prime is equal to times 2H prime. So the T will be a string which is twice of H. Okay, this is one thing that happens. The U here will do the same. We will have U is equal to 3 bar U prime, and U prime is equal to times 3 H bar. And finally we will have V equal 5 bar V prime. V prime is equal to times 5 H bar. H prime, sorry. So we have these 3 variable bindings that are done, and these 3 new variables, T prime, U prime, V prime. Then we have this merge call, so we'll have M is equal to the result of this merge call. Well, in this case, if I have U and V, the result will be 3, yeah? And I will have another recursive call here. Merge. Well, here I'm actually going to the next element of U, but I'm not going to the next element of V. So it'll be U prime V. Okay? And the final one, H prime here, will be, now I'm doing the merge of 2 and 3. T starts with a 2, and M starts with 3. So it'll be 2 bar. Let me write H double prime here. And it'll be again a recursive call. So I'm using here, I'm using the element coming from T, so it'll be T prime. But I'm still using M. I haven't used the 3 yet. Okay? So you see what happens? After, first we do 5 activations, then we will do 5 variable bindings. Here, 5. These, 1, 2, 3, 4, 5. And we will do 5 recursive calls. Times, 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 merge, merge. So when I do H prime dot 1, I start with 5 activations. They all execute the bodies in new threads. This causes 5 new variable bindings to happen. T, U, V, M, H prime. And it causes 5 recursive calls to happen. And those recursive calls will create new lazy suspensions. So 5 new lazy suspensions are created. So you see a lot of things happen. Okay? So when I do, let me summarize this. When I do browse H prime dot 1, I will start by activating 5 lazy suspensions. But they're activated in order. I don't know in advance. So it starts by activating the merge, and then the merge, when it executes, it needs its arguments, so it activates another merge, and another times. This merge needs its arguments. So eventually 5 are activated, one after the other. Then it will bind 5 variables. And it will do 5 recursive calls, which creates 5 new lazy suspensions. So this is everything that happens when I do H prime dot 1. Okay? This is a very simple thing. Huh? It takes me only 1 or 2 seconds to type H dot 1. But a lot of work is done, okay? Which is hidden inside, and you don't see it because it's all hidden inside. It looks like you have functions being executed simply, but because of the weight needed in the threads, connections, the activation happens in the opposite order, okay? So it starts by activating this one, then those, and then the information comes back. I bind the 5 variables, I do a recursive call, I create 5 new lazy suspensions. So if I make the final picture then, make a final picture here. After I do browse H prime dot 1, I will create, so H prime will be equal to 1 bar 2 bar H double prime, and this will create another lazy suspension, merge T prime M, because I have only used the T, I have not used M. So the T prime will create another lazy suspension, will be times 2 T prime. And then the M will create another merge. Now, look, that's very interesting. I've used the T here, the 2. But I have not used the 3 and the 5 yet, which means that this merge will actually be the same as before. Okay. Times 3h times 5h. So you can see it's possible maybe to optimize this. But here I'm looking at the perfect, just the execution, simple execution. So what happens is I activate them all, I bind variables, but remember, look what happens here. The t prime here, this is, the 2 is coming here, right? So the t prime is 2, the t is 2 bar t prime, huh? Like that. So this one will have a new lacy suspension. But notice I'm not actually using the U and the V yet. It's very dynamic. It depends on how the merge. Merge actually has different recursive calls. Huh? Inside the merge, there's different recursive calls. There's 3 possibilities. Either I use S1, I use S2, or if they're equal, then I use both of them. Okay? So there's different possibilities here. So it might be that I do a merge call here, okay, with where I'm not using stuff. Okay? So here I have then a new 5 lazy suspensions. Okay? So this looks somewhat complicated, right? This looks pretty complicated, the way I've shown all these executions. But it's important to understand how it works. Later on, when you use lazy in your career, when you know very well how it works, you don't always have to go to this level of detail, okay? But right now, when you're first learning it, it's very important to do this. So I expect you to be able to analyze a lazy execution in this way, okay? How it actually runs. Of course, you can be lazy and forget about all that and just annotate your functions with fun lazy, call them, and that's it, and it works, okay? It will work. But the execution might be lazy, but I don't want you to be lazy, okay? I want you to understand how it works, okay? So that's how the lazy suspensions, how they actually execute. Now, a little bit later, we're going to see a bigger example, lazy quicksort, where actually it's more subtle. And it's very interesting how to see it works. But it's important to see this in terms of the Hamming first. You can't always make functions lazy. Okay? So it's possible that the laziness doesn't help anything. Let me make some space. So let me talk about, give an example of a monolithic versus an incremental function. So a monolithic function is one where the laziness does not have any advantage, and an incremental function is one where the laziness does have an advantage, where you can compute things incrementally. So the Hamming problem is a case where all the functions are incremental, okay? So merge and times are incremental. But let me give you an example of a function that's not incremental, where the lazy does not have an advantage. There's many functions like this, huh? So here's a simple example. Let me do reversing elements of a list. So let me write a function. Reverse Let me do it with an accumulating parameter. So how does the reverse work? Well, we're going to use that. Question?
If the list is circular, it's like if the infinite.
If the list is circular, you're saying a list where the final element points back to the beginning.
Yeah.
Okay, I'm not talking about this kind of list now.
It's like an infinite circle.
It's like an infinite list. So circular lists. So the question is, what happens when you have circular lists? A circular list is a list that looks like this. For example, 1, 2, 3, L. Okay, where the L points back. So it actually looks like this. If you look at it, and you don't look at this, it looks like it's an infinite list that's always 1, 2, 3, repeating forever. That's what it looks like. Well, the answer is, this kind of list works very fine in a lazy program. Okay? You can use it with lazy programs. And sometimes it's good to use. But I'm not going to show it here. It's kind of outside the scope. Okay? It's more kind of a more sophisticated use of lists. So that's another advantage of lazy, that cycles don't give any problems, actually. Okay, so let me go back to reverse now. Let me show you a simple reverse function. So reverse of a list, case of h bar t, reverse, and this will return t h bar a. Okay, and I have nil, then nil. So this is a simple reverse function, okay? So if I call browse, reverse, and I have 1, 2, 3, and I give the initial value nil, this will display 3, 2, 1. Okay. That's reversed. You see, that's very simple. You know this. It's a standard kind of functional program. What happens if you make it lazy? What happens if reverse is lazy? Well, let's take a look. What happens if we make a lazy reverse? What about lazy reverse? So basically I'm going to add a fun lazy reverse. Okay? Let me make a lazy reverse. Let me do something like this then. L is equal to reverse 1, 2, 3, nil. And here I have a lazy reverse, okay? Lazy version. And then I do browse L dot 1. Okay? What happens now? It's very interesting to see what happens. So this creates a lazy suspension, as usual. So we translate it as usual, and it will work actually, but it will not give the result so nice as the other ones. You'll see why. So this will create a lazy suspension. So I have L, and here I have reverse 1, 2, 3, nil. Okay? So now I do browse L dot 1. So this will activate the lazy suspension. Okay? And it will do L is equal to the body of the reverse. Here, the case. No, this is 1, 2, 3, sorry. The argument here is 1, 2, 3, yeah? Right. In a nice way. Reverse of 2, 3, 1 bar nil. Okay. So it runs this. Okay, fine. So this will run. So H is equal to, we haven't gotten there yet. So it's T and then H bar nil. So this will run. The argument here is 1, 2, 3. The accumulator argument is nil. This is A. Huh? So to be very precise, we don't know yet what TH and A are. So this is the code. 1, 2, 3 will run. So this will actually call or make a recursive call. Reverse of T, which is 2, 3, 1 bar nil. Right? So this executing this code leads to this recursive call. Very fine. Now, so L is equal to this recursive call. So what's going to happen here? Well, note that the L.1, it's doing basically a wait on L. Okay? The dot operation here is doing a wait on L. And this is what triggers the wait needed here. Now this recursive call is going to create another lazy suspension. Right? Another lazy suspension, which will do a wait needed on L. But the wait needed on L will immediately run. So this will create lazy suspension. And the wait needed on L will immediately run. And the reason is because we already have a wait. Will not suspend, okay, the wait needed. Which means that this recursive call will run normally. It won't stop. It's because we have a wait on L, but we still don't know the first value element, okay? So the lazy suspension here will immediately run. It activates right away because the wait needed will not wait. Wait needed L is not going to wait. It's going to immediately go on because we have a wait on L. The wait on L, it's sitting there and it's waiting for an answer. You say, okay, I want an answer here. I want L to be bound. Okay, so we run we run this, L is still not bound. So we keep going. And in fact, it will keep going and it will execute the whole reverse. The whole reverse will be executed until the end. Okay? Except there will be some more overhead, no? Because of the lazy suspension. But it's going to execute the whole reverse. Because each time we activate here the lazy suspension, we execute, we're not getting a value for L yet. We don't get a value for L until the very end. Okay? Until the whole thing is done. So here, in the middle, we're not getting a value for L yet. Okay? So the result is the reverse will execute completely. And we will have at the very end, L is equal to 3, 2, 1. At the very end. We have the whole answer. And then, of course, L.1 is equal to 3. Okay? Now we're fine. Now the wait is happening. Okay? But it will actually execute the whole thing. Because each time we do an activation, it still does not bind L. You see that, huh? So the reverse, the lazy version of the reverse, it's going to work. It works fine, but it gives no advantage. So you see, adding the lazy annotation will not make a bug. Okay? That's nice. It will not have a problem. But it's not always giving you an advantage. So in this case, the reverse will execute the whole thing before it returns a value of L. And actually, it's kind of logical, huh? If I have reverse elements, and I'm asking for the first element of the reverse is the last element of the original list, okay? So it's clear we have to get to the very end of the list before we know the first element of reverse, okay? So it's kind of hard to do an incremental version of reverse. How would you do it? So it's not possible. So not all functions can be made incremental. So we say that reverse is a monolithic function because the laziness gives you no reduction in the computation. So lazy does not reduce the amount of computation. So in terms of recursive calls, in terms of the number of recursive calls are done, all of them are done when I ask for the first element. So we say reverse is a monolithic function, whereas merge times other functions are incremental. So this is actually a property of the thing we're computing. Reverse needs the whole list before you can give you the first element. It's pretty clear. You can't really make it incremental. Whereas the merge and the times are naturally incremental. Okay? So you see that? So the lazy, you have to be careful. It's not always giving you an advantage. It will not give you a bug. You see the reverse, it still works. The lazy reverse still works. Of course, it's going to have a bit of overhead here, because each time it's going to be creating a thread and running a wait needed. So it's going to be a little bit slower, but that's a constant factor. The complexity will not change. Okay? So it'll be a little bit slower, but it still works. Okay? Okay. So now that shows us a lot about lazy functions. Let me make now a small break, 5 minutes, and then we'll give you what's called, for the laziness, the pièce de résistance. I will show you a real example of the power of laziness, where the laziness is actually able to invent an algorithm. So the quicksort is not monolithic. It's incremental, but it's incremental in a very interesting way because it's going to do some computations to compute the first element or the first elements, not everything. And what it does is actually very interesting. So we're going to see that after the break. Let me now show you the lazy quicksort. But first of all, let me show you how quicksort works. So quicksort is a sorting algorithm that takes a list of elements. It takes one element, which is called a pivot. Takes one element, and then it splits the list into two lists. One which is all elements that are smaller, and the other one is all elements that are equal or greater than the pivot element. So you get these two smaller lists. One is all smaller than the pivot, the other one is all greater or equal. Then you recursively sort those two, and then you merge them, you append them together, and then you have the sort of the final. So here I take an element from L, and if it's less than X, I put it in L1. If it's greater than equal to X, I put it in L2. So if Y is less than X, then put in L1. Oops, sorry. Else, it's greater than or equal, and I put in L2. Okay? That. And when L is done, then I have L1 is equal to 0. So it's a simple recursive procedure. Okay, I traverse L and I put elements in L1 or L2. So So putting in L1 is doing something like this. It's L1 is equal to y bar M1, and then I have recursive call M X M1 L2. And here I put in L2, so I have L2 is y M2 M X L1 M2. So that's it. There's only one small mistake here, of course, which is what? What's the mistake? I made a mistake. Yes?
M1 is not defined.
M1 is not defined yet. So I have to declare M1 and M2. Exactly. So M1 I declare, M2 I. So this is it. This is the partition. This is the heart of the quicksort. Okay? So I can show you an example of this now. So let me make a partition. So I make a list. Somewhere in the list here. And a pivot element, let me make 4, L1, L2. Browse L1, browse L2. So you can see how the partition works here. So 3, 3, 2 is all the elements less than 4, and 7, 6, 5, 8, 5, 4 is all the elements greater than equal to 4. Okay? Let me also define an append. Append function, which takes two lists and appends them together. Okay, so it recurses down the first element, the first argument, and puts the x in the front, and then at the end of L1 it just returns L2. So it appends things together. So we need this for the quicksort. So let me just show how it works. So here's a simple append. 3, 4, 5, 2, 2, 2. It appends them together, it gives me one list. 3, 4, 5, 2, 2, 2. Okay? So now let me make the actual quicksort algorithm. L. So I have to call partition. So I need a pivot element. I'm going to take the first element of L as a pivot. I can also take other ones, but this is very simple. So X would be the pivot. Partition L, X, L, sorry, M. M, X, L1, L2. I have to declare here L1, L2. So I partition. So I take X as a pivot element. I partition the other elements, giving L1 and L2. Okay. Then I do recursive call. S1 is quicksort L1. S2 is like this. I append them together. Okay. So this is the quicksort algorithm. There's a small bug in this algorithm. There's a small bug here. So first of all, we have to be careful. The recursive call always has to have a list smaller than the original. So L1 and L2 have to be smaller, otherwise I have infinite loop. So is it true here? Are we guaranteed that L1 and L2 are always smaller than L in size? Yes or no? What do you think? So when you have recursive call, that's the first thing to check. That the recursive call is less, the size is less, strictly less. Is it true here?
Oui, parce qu'à chaque fois, on enlève le pivot de la
Chaque
liste.
fois on enlève le pivot. Yes. So here I have removed one element from L. So M is already one element shorter. So that means in L1 and L2 are maximum the size of M. So that's absolutely right. So we are guaranteed. There's only one other small problem here that we need to fix, is that pivot has to be part of the result. Okay? Yes?
Il y a des moyens de transformer cette fonction en l'optimisant pour la taille de récursion.
There are optimizations possible, but I'm not going to show them here. So there are other somewhat optimized versions of quicksort. But this is the most simple, straightforward version. And it's maybe not the best version, but it's the version I will show you because it will show you very clearly the advantage of laziness. I want things to be very simple here, okay? So I have to add, the problem is that I have to, X, I'm not allowed to remove it, huh? So X has to be in between L1 and L2. So if I put X bar L2 in the append, then I keep the X and then I'm fine, okay? So this is a correct quicksort algorithm, normally. Okay, so there's still a bug in there, stupid bug. I have to declare S1 and S2, of course, here. There. Now it's fine, right? See, even small programs can have lots of subtle little bugs. It's good now, right? So if I do like this, it doesn't look very good, huh? 3, 2, 3. Oh, of course, I'm very stupid. What did I do wrong here?
Faut ajouter X à la fin de L2 au début de
No, the error is much more stupid than that. What is it?
On n'utilise pas S1 et S2 dans les appels.
Exactly. So the append has to append S1 and S2, not L1 and L2, okay? It's a very stupid bug, huh? Nobody saw it. Strange. See, small program full of bugs, right? Now it should be fine, right? After all that, are you confident now that it's correct? You saw many, many bugs in this little program, huh? Wow, it actually seems to work, huh? I have a sort version here. Okay, now let me do a magic trick. I will make a lazy quicksort algorithm. So let me copy this. So the partition actually stays the same. Let me take append and quicksort and make them lazy. So let me create a lazy append, L append, the fun lazy, and a lazy quicksort, fun lazy, L quicksort, L quicksort, L append, like this. Okay? So let me do it this. Get rid of this. So this is a lazy quicksort. So first I have a lazy append. So when I do lazy append, it will not do anything until I need elements. Okay? Fine. Let me declare the lazy append. And now let me declare lazy quicksort. It's correct, huh? So the lazy quicksort, when I do a recursive call, L quicksort L1, for example, this will not do anything until I actually need the result. Okay? So let me try something here. Let me L quicksort. Here's an example. Browse S. So I call L quicksort. So this displays nothing, which is what we expect. It's a lazy function. Now, if I want the smallest element of the input, I can do this. I can do browse S.1. Okay? And this will cause the lazy suspension to reactivate. And the smallest element is 1. Okay? How much work did this algorithm do to get the smallest element? How much work did it do? That's an interesting question. How much work did it do? Because to sort n elements, the algorithm takes n log n on average, or even n squared if the list is in the wrong order. But in the lazy version, how much work does it do to give me the first element? So the smallest element. Well, let's see what happens. So I do S.1, okay? I want S.1 here. So let me go back and look at the code to the quicksort. So it will activate the lazy suspension because the S.1 does a wait on S. Huh? So the body will be executed. I will execute the partition completely. So partition MX L1 will be executed completely. Then I will create 2 more lazy suspensions for the recursive call to quicksort and the L append. Now the L append suspension will execute immediately because the wait needed is, there's already a wait on S. So the wait needed S will execute. So the L append will execute right away. And it will need S1. It needs its first argument. That means the first recursive call to quicksort will execute. Okay? So I do a partition on the whole list. And then, after a little bit of work, I'm going to call quicksort on L1. Okay? So you see what happens when I do browse S.1? I will do a partition on the whole list. And then, after a little bit of work, I will call quicksort of L1. The quicksort of L2 will not be activated, but the one on L1 it will be. So that will cause a partition on L1 to happen. And that will cause a new partition recursively, and things get smaller and smaller and smaller. Okay? So let me show quickly on the board what it's doing now. Let me make a picture on the board. When I do browse of S1, S.1, the work that's done. So basically I do a partition. So basically let me make the picture like this. This is the main list L, and I will partition it into L1 and L2. Okay, this is the partition. And then I will call quicksort of L1 recursively, only on L1. So this will do another partition, like this. L1 prime, L2 prime. And recursively, it will call it will only do the L1 part. Until we get one element. This one element will be, of course, the smallest element of the list. Okay? It's clear. The L1s are all smaller than L2. L1 primes are all smaller than L2 prime. L1 double prime is all smaller. So this one will be clearly the smallest element of the list. So how much work is this doing? So here I have a number of, how many operations? So assuming on average that the partition divides the list into two approximately equal paths. So that means the first step, I will do a constant times n, because assuming the length of the n is n elements. And then in the next step, I will do a constant times n over 2, and then a constant times n over 4. So the final result will be all the way up to 1 element. So this is 2cn. Right? I'm dividing the list into half each time. That means it's bounded by n. It's a constant times n. That means finding the smallest element of the list is order n, which is exactly what you would get if you write a program that only does that. If I write a program that gets the smallest element, I have to traverse all the elements. So the quicksort is actually incremental here, because it's not n log n when I only need the first element. It's giving me only one element, and it's order n. Okay, let me go back to the screen here. So this is done. This takes order n. What if I go what if I want to be a little bit more, let's say, clever? I want the smallest two elements. I have n elements, and I want the two smallest ones. Well, that's easy to do here. I just do browse s.1 and browse s.2.1. And the quicksort will give me that. It's 1 and 2. Okay? And I can go on. I can have the smallest 3 elements. But how much work does it do to give me that? Well, if I want the second element, somewhere here I'm partitioning and I have 2 elements left. So if I want the second element, the smallest 2, the amount of extra work is actually very small. Because when I partition all the way down, at some point the list L1 here is going to be very small. It's going to have 2 elements. And those are the 2 elements that I want. Okay? So getting the smallest 2 elements is only a little bit more work than getting the smallest element. Okay? What if I want more smaller elements? Fine. So let's say 4 elements. This is easy. I do S dot, that's the second one. 2, 1. So 1, 2, 2, 3. Okay, those are the smallest 4 elements. Okay, let me now go back to the board. So, in general now, what happens if I ask for the smallest k elements out of n? Okay, the smallest k out of n. Let's see. So, let me make a picture. How much work does it do? Okay, so let's say I want the smallest k elements out of n elements. Okay, That's easy when I write it. Huh? I just do a touch. I do touch for n for k. How much work is it doing? How much work is this algorithm doing? Well, we can actually figure it out. Let me show you a simple way to figure it out. So here's my original list L, n elements. Okay, and I divide it into 2. The way the system normally works is that these two are approximately equal, and each one is doing recursively a quicksort. So this one will be divided into 2, this one will be divided into 2, and so on. Okay? And so this one will be divided into 2, and so on. So that's how it works. And each time I will have half. Here I have n over 2, n over 4, okay? Well, if I keep dividing in 2, and each time I will do a recursive call to quicksort, okay? So when I have n over 4, I'm doing a recursive call to quicksort. That's reasonable, huh? At some point, I will have a very small list here. I'm each time dividing by 2, which has k elements. Or actually, the smallest value of n divided by power of 2, which is bigger than k. But let's say it has k elements. Okay? These are the k smallest elements. So at some point, when I keep dividing by 2, I will reach k. Not the k. And then I will do a recursive quicksort. Here. I will do the recursive quicksort for k elements, because I will need all of the k. I want the smallest k, I need all of them. So how much time does this recursive quicksort take? Well, it takes k log k. Because quicksort on k elements takes k log k. Okay, so how much time total does the algorithm take now? Well, we have to take k log k plus the time for all these partitions. So the partitions will be bounded by n, a constant times n. So the total time will be n plus k log k for getting the smallest k elements out of n. So if k is equal to 1, if it's like a small constant, then this would be order n. If k is equal to n, then this would be n plus n log n, which is n log n. Okay? If you remember complexity. So this is very reasonable. Now, how good is this? How good is n plus k log n? It's actually very good. If I want to find the k smallest elements out of n, an algorithm n plus k log n is actually doing very well. Okay? But it's even more than that. Suppose now, forget about quicksort. Suppose I ask you, invent an algorithm to find the smallest k elements out of n. How would you do it? That's not so easy, it seems, huh? Invent me an algorithm that does this. Well, the lazy annotation will automatically invent the algorithm because the quicksort is incremental. And it's actually a very nice algorithm because you don't even need to know in advance the value of k. If I ask you, give me an algorithm that gives the smallest 2 elements out of n, well, that's very easy. I just keep an array of 2 elements, I traverse the list, and I put the smallest 2 elements in that array, and at the end I'm done. But what if I need the smallest 3? Well, then I have to do over again, right? Question?
En fait, on rajoute de la laziness, on transforme nos structures de données en générateur. Donc ici, on génère une file de k éléments.
Right. So you're saying, using the laziness, we have transformed the algorithm into a generator of results. Yes, that's right. So if it's incremental, that's what we did. So the more elements we ask, the more computation it does. Yes. Okay. But then the question is, how fast is your generator? Okay? But in this case, The generator is doing very well. It keeps all the information needed so that you can always add more to k. If I ask you, give me an algorithm for the smallest 2 out of n, and you write me the algorithm, that's easy, right? I have an array of 2 elements, I traverse my list, and I keep updating the array. That's the simplest way. But what if, after it's done, I ask you, actually, no, I also want the 3rd one. And then, okay, so I need to do again, but with an array of 3 elements again now. Maybe I want the 4th and the 5th one. So you see, if you don't know in advance, that approach will not really work. Whereas this approach will work even if you don't know in advance. Maybe I'm looking at the smallest elements until I find an element that satisfies a certain condition. Well, this one will do the smallest amount of work for that. Okay? So you can see that this algorithms actually do very well. You see that? So laziness, if your function is incremental, it can actually be a very smart way of improving an algorithm. So if you want to build an incremental algorithm, try first to build a normal, non-lazy one, but try to make it as incremental as possible, and then make it lazy. And maybe you have already the solution. Okay? Okay, so that's just an indication of the power of laziness. So here laziness has invented a smart algorithm. Okay? See that? And in a later course, we're going to show how to invent smart algorithms, more algorithms that use laziness. So why are we doing all this, by the way? Why are we trying to make algorithms as smart as possible with laziness? Well, the reason is because they're all declarative. So they have all the advantages of declarative programming. Okay? Question?
Aussi, un des avantages, c'est que maintenant, on a une fonction qui peut servir de producteur pour un consommateur dans des tâches qui sont prévues.
A producteur consommateur. So now we have a producer consumer. Well, not really, because we have to know the end because of the partition. So you can't, the quicksort, you can't just keep feeding it more elements. Huh? You have to know the end. But that's normal, because what if a new element comes in which is very small, okay? Then all the previous results are not valid. So the quicksort here, you have to know, the n has to be known in advance. Huh? Of course, the n. Not the k, but the n. Huh? In fact, a sorting algorithm which does not know n in advance is actually not so simple, huh? Because it might have to correct mistakes from earlier if new small elements come in. Huh? So that's a different problem. Yeah?
Ce que je veux dire, c'est par ce producteur consumer, la liste n'est pas infinie, mais c'est enfin, la liste n'est pas infinie, mais ce que je veux dire, c'est qu'on peut très bien faire une tâche. Enfin, si on fait un quicksort, et puis qu'on a besoin d'appliquer quelque chose sur chaque élément de la liste privée, on peut le faire. Parallèle, on ne va pas attendre que le prix soit fini.
Oui, c'est ça. So in fact, yeah, so you can start getting results. Yeah, you can actually use this as a kind of a concurrent, parallel form of quicksort. That's another improvement you can do. You can start getting results even if the rest of the algorithm is not finished yet.
Oui, voilà,
yeah, that's another. I haven't shown that, but that also, and that's also an advantage of declarative, which I called concurrency for dummies. Huh? So you could execute the whole quicksort on multi-core, for example, and you can start getting results, small elements, even while the other parts are not finished yet. Okay?
C'est du dataflow à l'état pur. Le fait que.
Pardon?
C'est du dataflow à l'état pur, que le fait que il y a toujours un flux de données qu'on peut
The data flow, you're saying it's pure data flow. Why? Is it pure? I don't understand.
Parce que il y a toujours un flux de données qu'on peut traiter en parallèle. point.
Yeah, so you're basically writing, because all of the recursive calls to quicksort can be turned into recursive agents using dataflow. Yeah, that's true. Which I did not show, I just show laziness. But another thing you can do with the quicksort is all of the recursive calls can be made into concurrent agents. And they can be run in parallel on multiple machines in a distributed system. And the result is automatically correct. Okay? So the declarative formulation, it lets you parallelize things as well. So that's in addition to the laziness, huh? Those are two advantages, the lazy and the concurrency. Okay? So there's no worries about concurrency here. You don't have to worry about locking or any kind of monitors, no race conditions. There's no problems making this concurrent and running it in parallel. So that's a separate thing from laziness. Huh? So I'm saying that because of the question. Because here, you can actually have it which is both lazy and concurrent. You can run part of the system lazily and the other part concurrently if you want. So all of this with no race conditions, and which is one of the main advantages of the declarative model, concurrency for dummies. Okay, so that gives a lot of, I hope, a lot of intuition. So we have just a little bit more time today. Let me take a step back now. So we've talked about lazy, we talked about data flow concurrency, but it's nice to know exactly what it means. So I want to give you a precise definition of that, okay? So let me finish today, but I won't be able to do everything, but we have actually seen declarative functional programs that are concurrent. Okay? We've seen data flow, for example, the deterministic data flow. Which is a really excellent model. And when you start building big programs in your career, you should stay there as much as possible. And you will be able to get programs that run. Your boss will be very happy. You'll make lots of money, etc., etc. So this is a very good model. But what does it mean exactly? I want to give it the exact definition. So, remember, we have in functional programming, we have seen the Church-Rosser theorem. That means the result of the evaluation is the same for all reduction orders. Okay? Okay, for all reduction orders, and this is why concurrency for dummies, it works. Okay? Works because of this. So this we have seen. But we've seen it for lambda calculus. Okay? In our model, it's not exactly the same as lambda calculus. So we've seen this. Okay, this is something we've seen. But actually, our model is more general. So in the lambda calculus, you give an expression, you reduce, and it's done. Okay? So in the lambda calculus, you have initial expression, you reduce, and you get final expression. Okay? That's lambda, and the Church-Rosser work for that. But our model is actually doing more than that. We have a model where you can have an agent with a stream of input. Stream input and stream output. And you can keep feeding elements and more elements appear. And this is a concurrent agent. So we don't have one initial expression. You start with 5 plus 5 plus 5. Then 15, and it's done. One expression and one final expression. So you have a beginning and end. Here, in our model, there's no beginning and no end. You can keep giving information forever. And if you stop giving information, then the output also stops. So the thing is actually, there's no initial expression, there's no final expression. It's completely incremental. Okay? That means it's not exactly the same as lambda calculus. It's a little bit more. It's actually doing more. So this is the model we've seen in our courses so far. And I tell you, this model is declarative, it's functional, deterministic data flow. But I kind of hand wave. I did not actually define exactly what's happening. Because the advantage of functional programming comes from church routing. Confluence is what it's called. The same for all reduction orders. The result is the same. This leads concurrency for dummies. But why exactly? Because we don't have initial final. We have a completely incremental execution. So what I want to do now is give you a better definition of declarative concurrency. It covers, it allows for incremental computation. And it's still satisfying the church Russell, the confluence. So I want to say a little bit more. So I want to show you more precisely what's going on. This model here, deterministic data flow, is super powerful, super important, but it's actually doing more than lambda, because it's incremental. So how do we fix that? How do we explain it? So let me just give you one concept, one idea is called partial termination. In the lambda calculus, you start with an expression, you reduce, and it's done. So this is termination, okay? It terminates. The computation is done. It's over. But we don't have termination here because you give some information and you can always keep giving more information, okay? So partial termination, it means that you can have stops. You give some information on the input, you execute, and then you have a result, first result. But then you can give more information, and then you have a new result. And you can give even more information, and you get even newer results. And you can keep going forever. So for example, if I have a stream, if I have an agent that calculates the squares, 1, 4, like this. I give 1, 2, it calculates 1, 4. Now if I add information, 1, 2, 3, it will be 1, 4, 9. If I now make 1, 2, 3, 4, then I will add 16. So there's actually areas where the system is terminated, but only temporarily terminated. So I give information, 1, 2, and it gives me 1, 4, and then it stops. But it's not totally stopped, because if I give more information, I add 3, it gives more results. And then it'll be 1, 4, 9. And then it will stop again. So it can stop several times. So it has many terminations. I give information, it terminates. I can always give more information, then it terminates again and again. So these areas, in the theory, they're also called resting points. Okay? That means I give information to the system, I let it run until it's done. And then it's done. This is here. But then I can give more information, and then it starts up again until it's done again. Okay? So each time I give a little bit more information to the input, more information comes on the output. And each of these executions, each of these little squiggly arrows here, is like a single lambda calculation. Okay? So you can have infinite sequence of those. And the system, we say it has partial termination. Because when you terminate, it's not fully terminated. You can always start up again. Okay? So that's the basic intuition. But let me stop here. So next week I'll make it more precise. Then I'll start showing more sophisticated algorithms. Okay? So this is giving you then a precise definition of deterministic data flow. So why do I want to give you this precise definition? Well, it's because I want you to write as many programs as possible that are like this, that are purely like this, and that don't use state. If you can put as much as possible here, then you have incredible advantages. So we want to make it so you have as much as possible of your system is doing this. Okay? So that's why we need to define precisely what it is. Okay, so let me stop here. And so I will try to put the recording on YouTube.